All right, so today we're going to be taking a deep dive into AI.
Oh, yeah.
Specifically, we're going to be looking at these large language models,
Okay.
LLMs, as I think everyone's calling them these days.
Right.
Things like Mistral and Llama 2.
Uh-huh.
And we're going to be looking at how researchers are trying to make them run faster and more efficiently.
Cool.
You know, one of the things that you were particularly interested in was this technique called precomputing.
That sounds interesting.
And that can be applied to the first layer of a transformer model.
Okay, so before we get into the specifics of precomputing,
Yeah.
it might be helpful to kind of remind ourselves that transformer models are the architecture behind a lot of these large language models.
Right.
They're responsible for processing language, understanding relationships between words,
Yeah.
but they can be pretty computationally intensive. So making them more efficient is a big focus in AI research.
Yeah, so it's like we're trying to soup up the engine of a race car, you know,
Exactly.
to get even more speed and performance. But in this case, the race car is like a powerful AI model.
Yeah, and that's exactly what this paper we're going to be looking at is all about.
Okay.
It's called Transformer Tricks, Precomputing the First Layer
Okay.
by Nils Graef.
All right.
And it's in this really cool micropaper format,
Oh, really?
which I think is kind of a neat trend
Yeah.
that we're seeing more and more of, where people are just getting to the point,
I like
bite-sized research.
So what exactly is precomputing in the context of these transformer models?
Imagine you're baking a cake.
Okay.
Precomputing is like getting all your ingredients ready beforehand,
Okay.
like measuring them out,
Yeah.
chopping them up,
Right.
so that when you're actually ready to bake, you don't have to stop and search for each ingredient.
Okay.
So in transformer models, it means doing some of the calculations in advance,
Right.
storing the results so the model doesn't have to keep repeating them every time it processes text.
So instead of scrambling around for the flour and the sugar in the middle of the recipe,
Right.
it's all neatly laid out.
Exactly.
Ready to go, making the whole process much faster.
Yeah, exactly.
With it.
And the paper focuses on applying this to the first layer of the transformer,
Uh-huh.
which you can kind of think of as like the initial processing stage.
Okay.
And it goes into how this works for different kinds of transformer architectures,
Okay.
those with parallel processing and those without.
Now, the paper mentions terms like attention and FFN
Right.
when it's describing these architectures.
Right.
I'll be honest, I'm a little fuzzy on what those are. Can you give us a quick breakdown?
Absolutely. So you can think of attention as the model's way of focusing on the most important words in a sentence.
Okay.
It's like when you're reading a news article and your eyes are kind of drawn to certain keywords or phrases.
Right.
The FFN, or feed-forward network,
Okay.
takes the information that's highlighted by the attention mechanism and then processes it further to understand the meaning.
So attention is like highlighting, and the FFN is like, okay, now I'm going to digest and understand those things.
Okay, that makes sense.
Yeah.
Now back to these different architectures.
Yes.
The paper uses diagrams to show how pre-computing works in each case.
Uh-huh.
It's like having a visual roadmap.
Right.
Can you walk us through those diagrams?
So in models that have parallel attention and FFN, like in figure 1 of the paper, we can pre-compute the output of multiple steps at the same time.
Okay.
Think of it like preparing all the ingredients for your cake batter at once.
Right.
Now, for models that do attention and FFN sequentially, which is shown in figure 2,
Okay.
we can only pre-compute some of the initial steps,
Okay.
like maybe measuring out your dry ingredients first.
Okay. I'm picturing these assembly lines in my head now.
Yeah,
That makes it much clearer,
Right.
the difference between parallel and sequential processing.
exactly.
But the paper also points out that pre-computing doesn't just save computation time. It can also reduce the number of times the model needs to access its memory,
Right.
especially for small batches of data.
Can you explain why memory access is such a bottleneck for these models?
Imagine trying to find a specific book in a massive library.
Okay.
You have to search through countless shelves and stacks,
Right.
and that takes time, right?
Mm-hmm.
So similarly, when a transformer model needs a piece of information, it has to go search through its memory, which can be slow.
Right.
So pre-computing is like putting the most frequently used books right at the front desk.
Okay.
So they're immediately accessible.
So it's like having a shortcut to the information the model needs most often.
Exactly.
And it makes sense that it would be especially helpful for small batches of data,
Right.
kind of like quickly finding a book in your own personal library
Right.
versus having to search through the Library of Congress.
Exactly.
Now, of course, there's no such thing as a free lunch.
Right.
The paper does mention that pre-computing requires more storage space.
Uh-huh.
So how significant is this increase?
That's a great question, and you're right, there is a trade-off. When you pre-compute, you're basically storing those pre-calculated results.
Yeah.
And that does take up space.
Right.
And the paper goes into detail about how much additional memory different models require.
Yeah.
And what's interesting is that for a model like Mistral 7B, pre-computing only increases the memory footprint by a tiny 2%.
Wait, only 2%? That almost seems too good to be true. Why such a small increase for Mistral?
It has to do with Mistral's specific architecture.
Yeah.
It uses a type of attention called grouped query attention
Okay.
that lets it benefit from pre-computing without this big memory penalty.
So it's like Mistral has this built-in optimization that makes it super efficient even with pre-computing. That's pretty cool.
Yeah, it really showcases how these clever design choices can make a difference.
Okay, I have to ask about the bottom line here. The paper mentions some pretty impressive reduction factors.
Yeah.
For how much faster pre-computing makes these models for a single token. Pythia 6.9b can be sped up by a factor of over 11,000.
Wow.
What does that actually mean in the real world?
Those reduction factors are definitely impressive. They basically tell you how many times faster the model can process information
Okay.
with pre-computing. So in practice, this means things like faster responses when you're
Right.
talking to an AI,
Okay.
faster text summaries, overall better efficiency in anything that uses language processing.
Wow, so we're talking about a night and day difference in performance.
Yeah, you can think of it that way.
So you're telling me that by just pre-calculating some values, we can make these AI models thousands of times faster.
It's pretty remarkable.
That's like the difference between walking to the store and teleporting there.
Yeah, that's a great analogy, and it really shows why this research is so exciting.
Yeah.
Because these seemingly small tweaks can have such a big impact on how we use AI in everyday life.
It makes you wonder if pre-computing the first layer is so beneficial.
Right.
What about applying it to other parts of the transformer? Could we unlock even more gains?
That's a great question, and one that I think researchers are actively exploring.
Mm-hmm.
The fact that this paper gives us the code they used is kind of an open invitation for others to build on this work.
I love that collaborative spirit.
Yeah, me too.
So to our listener out there,
Yeah.
if you're intrigued by this idea of making AI models more efficient, I encourage you to check out the paper's code
Absolutely.
and maybe even try experimenting with pre-computing yourself.
It's a really cool area of research, and who knows, maybe you'll discover the next breakthrough.
Okay, so the paper focuses specifically on transformer models that use ROPE,
Yeah.
which stands for rotary position embedding.
Uh-huh.
So what exactly is ROPE and why is it relevant here?
ROPE is all about encoding the position of words in a sentence, which is super important for these transformer models to understand the order and context of language.
So it's like giving each word a specific address within the sentence so the model knows where it belongs?
Exactly.
So how does that tie into pre-computing?
Because that positional information is kind of static and calculated beforehand.
Okay.
We can pre-compute those initial layers that rely on it.
Gotcha. So if the positions were always changing, pre-computing wouldn't really work.
Right, it wouldn't be as effective.
It's like knowing the seating chart in advance so you can set the table ahead of time.
Exactly.
Okay, I want to circle back to those impressive reduction factors we talked about earlier.
Yeah.
The paper mentions different factors depending on the batch size.
Uh-huh.
Can you explain what batch size means and why it matters for pre-computing?
Batch size is basically the number of sentences that the model processes at once.
Poke.
It's like having multiple ovens baking cookies simultaneously.
Gotcha.
Larger batch sizes are usually more efficient, especially when we're training the model,
Okay.
because you can parallelize things.
So how does pre-computing play into this?
Pre-computing really shines when you have smaller batch sizes,
Okay.
particularly during this process called autoregressive text generation, where the model is predicting one word at a time,
Right.
and each word needs to access memory for calculations.
Yeah.
So having those values pre-computed really speeds things up.
So it's like having all the ingredients prepped and ready to go,
Right.
instead of running back and forth to the pantry every time you need something.
Exactly.
I'm starting to see how all these factors are connected, the pre-computing, the batch size, and the specific architecture of these models.
Yeah, it's a really fascinating interplay.
It shows that optimizing these models isn't a one-size-fits-all thing.
Right.
It requires understanding the underlying mechanisms and really considering the task at hand.
Absolutely.
Now, the paper highlights a few real-world examples of these models, things like Pythia Mistral and Mixtral.
Yeah.
What makes these models interesting from a pre-computing perspective?
They each showcase different architectural choices and how pre-computing can be adapted to those specific designs.
Okay.
So for example, Pythia uses a parallel architecture, so you can do more extensive precomputing with that,
Okay.
compared to Mistral, which has a serial approach.
Mm-hmm.
And then you have Mixtral, which is this mixture of experts model,
Right.
which presents its own unique challenges and opportunities.
So it's not just applying pre-computing blindly. It's about understanding the strengths and weaknesses of each model
Exactly.
and then tailoring the approach accordingly.
It's like custom fitting a suit.
I like that.
You take those measurements, you make sure everything fits perfectly.
And this brings us back to that question we had earlier
Yeah.
about could we extend pre-computing beyond just the first layer?
Right.
The paper doesn't explicitly explore this, but it definitely lays the groundwork for future research.
Yeah, it's like opening a door and inviting us to step through and see what's on the other side.
So if we were to speculate,
Yeah.
where do you see the most potential for expanding pre-computing within these models?
Well, one area could be within the attention mechanism itself.
Okay.
Remember, that's where the model is figuring out the relationships between words.
Right, like it's scanning the text and highlighting those key connections.
Exactly, and that's a computationally intensive process. So being able to pre-compute some parts of that could lead to big gains.
Okay, and what about the feed-forward network?
Yeah, that's another potential area you could pre-compute certain calculations within the feed-forward network.
So it's like we're fine-tuning the engine, looking
Yeah.
for ways to optimize every single step.
Absolutely, and as these models get bigger and more complex, I think this will only become more important.
Right, because we want these powerful AIs, but we also need them to be efficient.
Exactly, and techniques like pre-computing and all these new innovations that are still to come,
Yeah.
they're going to be crucial for making AI a seamless part of our lives.
It's an exciting time to be following this field. I don't know about you, but I'm feeling pretty inspired right now.
Me too. It's amazing to see how much progress is being made.
Speaking of progress, I think it's time to wrap up our deep dive.
Okay.
But before we do, I want to give you a chance to leave our listener with one final thought to ponder something that really captures the essence of what we've been talking about today.
I think the biggest takeaway is that even in a field as complex as AI, sometimes the smallest changes can have the biggest impact.
Yeah, it's really cool to see that.
Like pre-computing might seem like this little technical detail,
Right.
but it can totally transform how these models perform.
It shows that you don't always need a massive breakthrough to make real progress. Sometimes it's about taking what we already have and finding those clever little tweaks.
Exactly. And for anyone listening who's interested in AI,
Yeah.
this paper is a reminder that understanding the fundamentals is so important.
Yeah.
It's about taking the time to learn how these models work at their core,
Right.
and then thinking creatively about how to improve them.
It's like figuring out all the shortcuts and secret passageways in a complex building.
Right.
Once you understand the layout, you can navigate it so much more efficiently.
Exactly. And what's cool about research like this
Yeah.
is that it opens up a whole new set of questions. It's like
right.
we've just scratched the surface.
It's like they've given us a map to this uncharted territory and said, go explore.
Exactly.